Hello everyone and welcome to lecture. Today we'll be talking about infinite sequences and infinite series and some basic applications of both of these. So we'll start by talking about an infinite sequence. And the main definition of an infinite sequence is that we can think of this as a function from the natural numbers into the real numbers. This is typically what we think of when we think of an infinite sequence. You can also think of infinite sequences that are more complicated, that go into other mathematical sets, like the complex numbers, or even other types of more complicated sets. But typically, when you hear the word infinite sequence, this is an infinite sequence of real numbers. So one way of writing this is our function notation. But the idea is that typically we just write an infinite sequence in the following notation. We can use the bracket notation, where we write a bracket to denote the start of the sequence, and then you put A sub k, which stands for the kth element of the sequence of numbers. And this is sometimes all that's written down. Sometimes we can denote the starting point of the sequence. This is that k starts at, say, typically we'll start at 1, but you can really start at any value you want to. And this goes on all the way to infinity for any value of k. So what this stands for is, say, an infinite list of numbers, like A1, A2, A3, and so on and so forth. An interesting note is that finite sequences are sequences that stop at some value are actually included in this this expression right here. Because what we could say is that for any finite sequence from 1 to n, you can write the finite sequence as a unique infinite sequence. You can write it as A1, A2, A3, all the way up to AN. And then just zeros all the way down for the rest of the elements. So in shorthand notation, we write this as AK, and K equals 1, and then stopping at n. So in applied math, the idea is that we're typically interested in the limit of the sequence, which may or may not exist. Because typically our application is going to be to, that limit is going to mean something. It's going to be very important. So let's go through and see an example of this that is actually very important to think of. This is you can think of this as a motivating example. I like providing motivation as much as possible with why you would learn something in mathematics for applications. So this is a good motivating example. Consider the following. Consider the decay of some drug in your bloodstream. This could be a cancer drug or some other form of drug. But when you take a drug, the amount of drug is going to decay at a certain rate in your bloodstream, and I guess what we'll think of is maybe we're taking the role of a nurse giving a patient a cancer drug. So this decay can be modeled in a number of different ways, but one of the most straightforward decay models that we know is exponential decay. So what we'll do is we'll say that the amount of the cancer drug decays in the bloodstream exponentially, possibly. This is modeled by the following differential equation, as we know, we've talked about previously. The rate of change of the amount is equal to lambda times the current amount if the amount is a function of t, is the amount of drug in the bloodstream at time t, and lambda is the rate of decay. And we know that we've seen that the solution of this separable differential equation is the amount as a function of time is equal to the initial amount times e to the lambda t, which for a constant initial amount and constant value of lambda, lambda is negative, gives you an exponentially shaped, so it hits the initial condition, and then there's an exponentially shaped curve that is your solution curve. Now the question is, typically when you're giving doses, you give multiple different doses on a fixed period of time. So we can ask the following question. We can say, well, what does the concentration look like if the half-life of decay is 5 hours, and you administer 100 milligrams of the drug during every one of these periods, so after every 5 hours. Now we can go through and directly see this very, very nicely. Let's say you have this initial dosage right here, say, y here. This corresponds to dosage as a function of time. So initially, we have an initial condition of A naught, which is, say, this concentration of the drug, or this amount of the drug right here. And then at this initial concentration, right, after, as time starts to go, the drug decays exponentially until it reaches this point right here, which is 5 hours, because that's the half-life of the drug. We then administer another dosage, which will push the drug up to 1, 2, 3 to right here. This value right here is A naught over 2, which is this distance right here, plus a new dosage of the drug, which is A naught. And then at this point right here, once the drug hits this dosage right here, it ends up decaying again for until it reaches half of this value right here. Corresponds to this right here. So this value right here, this distance, is half of the total distance here. That's half of A naught plus 1/2 A naught. And we have another dosage that happens at this time right here. So then when the dosage happens at this time right here, you have to add to this another dosage. So it'll be 1, 2, 3. And this process just continues to repeat itself every 5 hours. This gradual just sort of halving. And then, redosing every 5 hours. And what you're seeing here is that we have two different sequences that we're interested in, and two different sequence limits that we're interested in. The first one is the limit of the max concentration. Right. This max concentration we're seeing is getting larger and larger and larger and larger as you kind of continue to dose every 5 hours. And the reason that that's kind of a problem in some sense is that, well, we need to make sure that that this max concentration stays below any toxicity threshold for the drug, right? At some point, maybe we'll say this value right here, call it MT, for toxicity threshold, right? If the value of the concentration goes above that value, then the drug is going to become toxic to the person who's taking the drug, or too toxic to the person who's taking the drug, and that would definitely not be good. So the idea is that this is one of the big reasons why we're interested in the limit of the top sequence, and also we're interested in the limit of the bottom sequence. because the drug is also going to have an effectiveness threshold as well, and you want to be above that effectiveness threshold in order for the drug to be effective. So let's say, for instance, the effectiveness threshold is like this value right here. If this low, the limit of these lower values, the minimums of the concentration, are not above the effectiveness threshold, then the drug's also not going to be as effective as it could be, because it's essentially going to be like giving a placebo if it's not above that effectiveness level. So the concentration sequence here, we can actually write down in a very simple manner. This is actually as what we're going to do is, before we write the sequence down for this example, and throughout the lecture we'll call this the concentration example. And we're going to refer to this as the concentration example. So the first type of sequence that we have, and then we'll talk about, is called a recursive sequence. Really, there should be maybe classifications as well of sequence. You could call it classifications. So we have two main types, or I should say ways of writing sequence. Types or ways of writing. Because really, a lot of times you can kind of you can write a sequence in multiple different ways. I'll say ways to write a sequence. And the first way is what's called recursively. The second way is called explicitly. Now, for a recursively defined sequence, what that means is that you have, say, an initial value or possibly multiple different initial values in the sequence. So you're given, say, A0, and then you're given following terms in the sequence as a function of previous terms. So you're given, say, that AK is equal to some function of AK minus 1 for every single value of K. For K equals 1, 2, 3, and so on and so forth. So this is why we call this type of sequence recursive, because it's like each term in the sequence is determined directly by the preceding term in the sequence. And you can consider more complicated types of recursive sequences that depend on more than just one previous value. But for our purposes, we're just going to deal with sequences that are recursive and depend on one previous value. And we'll kind of deal with these recursive sequences first, and then go back to explicitly defined sequences a little bit later. So let's keep this down here for the future. So if f is a continuous function, then this limit can sometimes be evaluated, the limit of the sequence. And we can actually get a condition that has to hold if the limit exists. So if f is continuous, we know that the limit passes through the function, so we can take the limit of both sides of this expression and they should go to the same value. Specifically, if the limit exists, so, and the limit of the sequence exists, then the limit as k goes to infinity of ak should be equal to the limit as k goes to infinity of f of ak minus 1. The limit as k goes to infinity of ak, if the limit exists, is equal to some L. Because f is a continuous function, the limit passes through this continuous function. And this becomes the function evaluated at whatever that limit is. Because the limit as k goes to infinity of ak minus 1 has to be the same thing as the limit as k goes to infinity of ak, of the original sequence. So we get the equation that L is equal to f of L, which is in general a nonlinear equation, but if you can solve that nonlinear equation for L, you'll have the solution to all possible limits of the sequence. So this gives you solution of this equation, gives all possible limits. Of the sequence for a given recursive sequence. We'll see a couple examples of this a little bit later on in the lecture. But I want to get back to our concentration example and show exactly how we can view this as a given sequence. Specifically, it's a recursive sequence, and it's the following recursive sequence. The initial concentration is A naught, which is 100. You can think of A naught as the initial dosage, and we're going to treat it as the repetitive dosage, where we're going to apply the dosage at every 5 hours, which is the half-life of the drug in question, say. So then the sequence, AK, becomes the following recursive sequence. AK, for the dosage at the kth administration of the drug, is going to be 1/2 AK minus 1 plus A naught. This is a formula for the recursive sequence for the top, right, or the maximum concentration. At every new dosage, the new dosage is going to be 1/2 the previous dosage plus the value of the new dosage, A naught. So the idea here is that this equation is giving us exactly what we need, and it's telling us that this is exactly the correct relationship for this sequence of administrations of this drug. Now if you take the limit of both sides, so you apply this procedure right here, which we can definitely do because the function f of x 1/2 x plus a naught plus 100, this is definitely a continuous function that we can take the derivative of. It's differentiable 2 times, and it's a nice linear function. So because it's a continuous function, we can think about looking into whether this limit exists. And if it does exist, then the limit of the left-hand side, the limit of ak as k goes to infinity, that has to equal L, and it has to be equal to the limit of the right-hand side as k goes to infinity, which will end up being 1/2 L plus a naught. This is just equal to the limit as k goes to infinity of the right-hand side, which is 1/2 ak minus 1 plus a naught. And what we have here is exactly this equation. It's the equation that L is to equal 1/2 plus a naught. And if we solve right for L here, we get that L minus 1/2 L is equal to a naught, or 1/2 times L is equal to a naught, which lastly means that this limit L has to be equal to 2 times a naught, or 2 times the initial concentration, which means that that limit that we talked about before of the sequence before, so this, the limit of this maximum sequence of values right here, because that's what this sequence is describing. It's this top sequence of values. This limit is directly equal to just 2 times the initial concentration. So this highest value right here is just 2 times the initial concentration. It's definitely not to scale here because I'm just kind of drawing freehand right here, but if you end up drawing this out and looking at a direct plot of this, this is exactly what you see. So that's what this highest value is, which is really, really nice. And the idea is that we have this kind of direct relationship. So you can say that if you have some, mortality level for the drug or toxicity level for the drug, you want to keep this L 2 times a naught way below that high value, the toxicity level of the drug. But you can do this procedure as well for the lower limit as well, and try and make sure that's above the effectiveness level of the drug. This is a really good example of sequences, and like how a real world example of how you might really care about a given sequence. Let's do one more example. And then we'll talk about explicitly defined sequences. Consider the sequence AK is equal to AK minus 1 cubed. And we ask for what values of A naught will this sequence converge? Now again, it's no surprise. You look at this function right here. This is saying that the kth element of the sequence is the k minus first element of the sequence q. This function is a function of x, and it's a continuous function of x because it's just x cubed. So what we expect then is that the limit of the right hand side as k goes to infinity of ak is equal to the limit as k goes to infinity of ak minus 1 cubed. If this limit exists, it'll be equal to L, and if this limit exists, it will be equal to L cubed, which gives us the equation L cubed minus L, or L times L squared minus 1 is equal to 0. And this equation is an equation that gives us all of the possible limits of this sequence, because the solutions of this equation are we have three numbers. It's a cubic, and the first solution is L equals 0. And the other two solutions are L equals plus or minus 1. So and those are all possible limits then of this infinite sequence, this recursive sequence right here. So we want to figure out, how does A naught depend, or I guess determine what limit we're dealing with here. So if we draw a number line, we can investigate relatively quickly and see how it does depend. So it turns out that this sequence is going to be convergent to a limit, the limit of 0 specifically, if you take any value in the open interval from -1 to 1. So it converges to 0 if that initial condition is strictly less than 1 or strictly greater than -1. If you think about it, you take 1/2 as your A naught, and 1/2 cubed is going to be 1/8, and 1/2, that's basically going to be here. Right, remember, we calculated this by taking the cube of the previous value. So if your A naught, your initial value is 1/2, 1/2 cubed is going to be 1/8, and then you'll have that this value cubed is going to be 1/8 cubed, and so on and so forth. You see that the denominator is getting larger and larger and larger. So this sequence is definitely going to 0. And that's true for any value in between -1 and 1. But then at 1 and -1, it converges to each of those values. So it converges to 1 if the initial condition is equal to 1, and it also converges to -1 if the initial condition is equal to -1. You can see that for both of those, I'll just look at the -1 one. But if you say look at initial value of -1, -1 cubed is going to be -1, -1, and so on and so forth, all the way down the line. So therefore, if a naught is equal to -1, the sequence just converges to -1 because it's a constant sequence. It stays at -1 for every single entry. The last thing that we have is that it diverges. For any a value greater than 1, strictly greater than 1, or any a value less than 1. The limit's positive infinity. And so it diverges for any of these initial conditions. The limit is equal to 1 for this value right here. Diverges. The limit is equal to 1. Oops, the limit here should be -1. And the limit's equal to 0 for any a naught value in here, the initial condition. You can see why it diverges as well for any of these values. It's the same thing here. You'll just get larger and larger and larger values every time you cube the previous value. So this is a really good example showing how to deal with recursive sequences and how to use that expression for the limit before that you get if you have a continuous recursive sequence. So these are two examples that we've seen now of writing sequences in an implicit manner, or in a recursive manner. To write sequences in an explicit manner, what this means is to essentially write the sequence in terms of a direct function of the index of the sequence. So specifically, that a sequence is written explicitly if you can directly find ak, the kth entry in the sequence, as a function, some function directly of k, like the kth value in the sequence. And in which case, figuring out the limit of the sequence, or all possible limits, is the same thing as figuring out the limit of this function, gk itself, as k goes to infinity. So for example, the sequence ak is equal to 3 plus k divided by k plus k over k plus 1. Okay, this is where our function g of x here, g of k, is directly related with the function g of x, 3 plus x over x plus x over k plus 1, or x plus 1. So, well, we have a number of different properties that I'll summarize at the end of the video. The main property is that if the limit of this sequence as k goes to infinity is going to be the same thing as the limit as x goes to infinity of the function 3 plus x over x plus x over x plus 1. And we know that this limit can be evaluated by applying our limit laws. First, the sum limit law. And then we can use what's called L'Hopital's rule to evaluate the limit of both of these two functions. This first function, its limit is going to be the limit as x goes to infinity of the derivative of the numerator over the derivative of the denominator, because this is an indeterminate form for which we can apply L'Hopital's rule to. So this will be 1 divided by 1 plus the limit as x goes to infinity of this also is an indeterminate form. So this limit is going to be the limit of the derivative of the numerator over the derivative of the denominator, which is again 1 divided by 1. This is going to be 1 plus 1, or 2. So the limit of this sequence as k goes to infinity is also equal to 2, because ak is directly determined by this function right here. It's doing the same thing as its argument gets larger and larger and larger. This is one nice example of a relatively simple, explicitly defined sequence. For the concentration example, things get a little bit more complicated when we start talking about the limit as k goes to infinity, and I should say the direct explicit form of the sequence. But if we go through and try and do this, we can directly do this. You know that for the concentration example, ak is equal to 1/2 ak minus 1 plus a naught. And if we just kind of recursively keep plugging in the recursive definition of this sequence, well, we know that this is the same thing as 1/2 ak minus 1 is the same thing as 1/2 ak minus 2 plus a naught plus a naught. You just plug in here that ak minus 1 is the same thing as 1/2 ak minus 2 plus a naught. And so what we've seen, what this shows us is that ak is equal to 1/4 times ak minus 2 plus 1/2 times a naught plus a naught. If we do this again, so if I plug in again that ak minus 2 is the same thing as 1/2 ak minus 3 plus a naught plus a naught, or plus it's 1/2 a naught plus a naught. So I'm just plugging in here that ak minus 2 is the same thing as a 1/2 ak minus 3 plus a naught. This gives us that ak is equal to 1/8 times ak minus 3 plus 1/4 times a naught plus 1/2 times a naught plus a naught. And what you're seeing here is that if we continue this process of plugging in and continuing to substitute in the substitution, that the recursive substitution that's defining the sequence, we get exactly that. Inevitably we'll get down to the final value, which is 1/2 Right, this right here is 1/4 is the same thing as 1/2 squared. This 1/2 is the same thing as 1/2 to the 1. And then the coefficient of a0 in each one of these terms is the same thing as 1/2 to the 0. So eventually what we'll get down to is we get that this is the same thing. The kth term in the sequence, if you go all the way down to k equals 0, you'll get that 1/2 to the k times a0 plus 1/2 to the k minus 1 times ak minus 1 all the way down to 1/8 times a0 plus 1/4 times a0 plus 1/2 times a0 plus a0. This summation is exactly the correct way of writing this concentration example in terms of a0 itself. Oops, and this right here shouldn't be k minus 1, but it's just a0 here. Or, in terms of our summation notation from before, this is going to be the summation from k equals, well, actually, I'll use I as our index of summation. We need a new index of summation. It's the summation from I equals 0 to k of a0 multiplied by 1/2 to the I. So you're seeing that sometimes for certain types of recursively defined series involving when you do the reverse substitution, if you go from a recursive definition or the recursive way of writing the sequence to the explicit way of writing the sequence, you get summations that pop up in terms of this new definition. What this means is that for any value of k, the kth concentration is going to be the sum of a0 plus 1/2 a0 plus 1/4 a0 and so on and so forth, all the way up to 1/2 to the k times a0. And what this means for us directly is that if you want to, say, figure out the concentration at a given, the exact concentration at a given value of k for the explicit form of the sequence, you're going to have to compute this sum. And this also means that it's an interesting example, because if you say want to take the limit as k goes to infinity of ak, this necessarily means that we have to consider an infinite sum of values, the sum from I equals 0 to infinity of a0 times 1/2 to the I, and see what this infinite sum of values converges to. And it turns out that this is actually a very special example of a series. This is what's called a geometric series. Maybe I'll rewrite this with 1/2 here to the power I to make this look a little bit nicer. This is what's called a geometric series for this example. An infinite geometric series. This is called a finite geometric series for any finite value of k. And it turns out that there's a very specific condition for which we can actually define convergence of an infinite series of real numbers. And the infinite geometric series also, right, it's a very special example of how we can go through and figure out when it converges and when it doesn't converge. So we'll get into series a little bit later in the lecture. But these are two really good examples and kind of motivating examples for going forward. rigorously speaking, we can actually define the limit of a sequence. It has an exact mathematical meaning, and the mathematical meaning is actually very, very nice. It's a very kind of straightforward condition that has to hold if a given sequence does in fact converge. Let's say we have a sequence with a bunch of values 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on and so forth. Let's say the sequence initially starts far away from the supposed limit and just kind of gradually gets closer and closer and closer to the limiting value, where once we get high enough, the sequence really starts approaching that limit right there. So the mathematical definition of a limit existing is very similar to the limit for functions. Rigorously speaking, we say that the limit as k goes to infinity for a sequence is equal to L if the following definition is true. And this is that for any value of epsilon, positive value of epsilon, there is a point in the sequence. We'll call this point n, such that for all values or points in the sequence greater than or equal to n, the distance between the kth value and the limit is less than epsilon. It's within that epsilon. So for example, we'll draw the epsilon tube as this right here. So this is L right here. This black line is L. This is L plus epsilon, L minus epsilon. You see that for this example, that m value is 7. At the point m equals 7, all values of the sequence are staying within that epsilon tube, or the value of the sequence is minus L, the distance between the limit and the kth term in the sequence, for all k greater than or equal to that m value is less than epsilon. So what this statement is saying is that no matter how small that epsilon is, right, for any value of epsilon, no matter how small you want to make that epsilon tube, the sequence, there'll always be a point in the sequence where it starts to stay within epsilon of the limit. This is what it means exactly for a limit to exist and be equal to L. And this is what you have to use if you want to prove any properties of the sequence. But the idea is that using this property, we can prove a number of different rules and properties for sequences if the limit of the sequence exists and converges. And these properties are very similar to limits for functions as well. So the first property is the sum / difference property. This is that. This is if the limit as k goes to infinity of two separate sequences, we'll say ak and bk exist and are equal to values. A and B say, we can always say that the limit as k goes to infinity of ak plus bk is the same as the sum of the individual limits of each, and this is sum or difference. It's either or here. So I'll just denote that. Which is going to be a plus or minus b. This is one relatively simple computational tool that we now have at our disposal, and this comes directly from the exact mathematical definition of the limit. You can prove this. Next one is the constant multiple rule, which says that if c is any constant real number, that the limit as k goes to infinity of c times ak is equal to c times the limit as k goes to infinity of ak, which would just be c times a. And this holds for any sequence that has a convergent limit. These are sometimes called the basic limit laws. The next limit law is the product limit law. Which says that the limit as k goes to infinity of ak times bk will always be equal to the limit as k goes to infinity of ak times the limit as k goes to infinity of bk, which is a times b. And the last limit law that we have is that what's called the quotient limit law, which is that the limit as k goes to infinity of ak over bk is equal to the limit as k goes to infinity of ak divided by the limit as k goes to infinity of bk, or a divided by b, as long as b is not equal to 0, because we can't divide by 0. These four properties allow us to manipulate sequences and deal with sequences and determine sequence limits. So these are sometimes called the basic limit laws or the algebraic laws for limits. There's some very nice properties that we can use to simplify. In addition to these properties, we have several other properties that are very important that can kind of help us determine the limits for sequences that are very similar to the limit properties for functions as well. So if you remember from Calculus 1, there was this rule called this limit law called the sandwich theorem for functions, for limits of functions. This also applies for sequences. So if you have two sequences two sequences AK and BK such that the limit of AK is equal to L, say, and the limit as k goes to infinity of BK is also equal to L, and you have that for every single value of AK and BK, AK is below some other sequence CK, say, and CK is below some other sequence BK. If this is true for all values of K, then we can go through and definitively state that, well, because the limit as K goes to infinity of AK is equal to L, this has to always be less than or equal to the limit as K goes to infinity of CK, which always has to be less than or equal to the limit as K goes to infinity of BK, which is also equal to L. So that means that the limit as K goes to infinity of CK will be less than or greater than or equal to L and less than or equal to L, which means that it's squeezed in between these two. This is also sometimes called the Squeeze Theorem. So if you can squeeze an unknown, possibly very complicated function in between two other functions or two other sequences that are convergent, have convergent limits, and converge to the same value, you can automatically conclude that that sequence in the middle has to have the same limit, because it's essentially squeezed between the upper sequence and the lower sequence. So we've already kind of seen an example of this, but I just want to emphasize that we can use L'Hopital's rule for finding sequence limits as well. Alright, specifically this is because if you have a sequence that's defined explicitly in terms of some function g, the limit as k goes to infinity of that sequence will be identical to the limit as x goes to infinity of the function g of x. So let's say you have two separate sequences, one of which is going to zero, and we'll say the other one is also going to 0. So the limit of, say, some BK sequence is equal to 0. Well, then the limit as k goes to infinity of AK over BK is the same thing as the limit as x goes to infinity of whatever the function is determining AK plus g of x, and maybe the function determining BK is h of x. The same thing as then the limit of g of x over h of x, which is something that we can definitely apply L'Hopital's rule to if this is an indeterminate form, because the limit of g of x is 0 and the limit of h of x is 0. And also you also have to have that for L'Hopital's rule, h prime of x is non-zero for points around the point that you're calculating the limit at, in this case, as you go to infinity. So it has to be a non-trivial function. But the idea here is that this then can be directly calculated when we use L'Hopital's rule as the limit as x goes to infinity of g prime of x over h prime of x. This is another property that we can directly use to help us figure out general limits. Another property we can use is what's called the monotone rules, or monotonicity of a sequence. So this is saying that if a sequence is increasing, so that for monotone, ak plus 1 is greater than or equal to ak for all values of k, and it is bounded, then the limit as k goes to infinity of the sequence exists. Picture kind of, I'm not going to prove this, but this directly comes from, I can use the definition of sequence and the property of increasing and bounded to show this. So if a sequence is bounded above by some value m, say, and it's always getting, let's say the same height, but it's always getting less than, maybe a little bit larger, and then maybe it stays at this height right here. And the limit of the sequence is going to be this value L. And even if it keeps approaching m, it can never go larger than m, because if it's bounded by m. So a bounded sequence that's increasing will always have a limit. The same is true for decreasing, if it's decreasing, because boundedness implies typically that there's this m, right? M applies both on the top and on the bottom. Boundedness means that there exists some m such that the absolute value of the sequence will always be less than or equal to that value. So if it's increasing or decreasing, which is that ak plus 1 is less than or equal to ak, and it's bounded, then the limit has to exist. And lastly, we have there's a couple, specific special sequence limits that are good to know. So this is it for the properties. It's also good to know a number of different specific sequence limits that sort of pop up in general many different times throughout applied mathematics and throughout the study of sequences. So we want to look at those and kind of see those and get used to calculating, or at least when you see those limits, you want to kind of know where they come from and also how to use them when you're going through and calculating limits. So some commonly occurring limits that you see very often are the following. These are just some very straightforward examples. if we were to say take the limit as k goes to infinity of the natural log of k over k, this is going to be equal to 0. You can go through and show this using L'Hopital's rule, right? The limit, this limit right here is going to be the same as the limit of the function ln of x over x, which from L'Hopital's rule will be the limit as x goes to infinity of 1 over x over 1, which is the same thing as the limit of 1 over x as x goes to infinity, which is equal to 0. So all of these limits are similar to this, and you can use the various forms of L'Hopital's rule to figure out what the limit is going to be. For instance, the limit as k goes to infinity of k to the 1 over k, or the kth root of k. You can use L'Hopital's rule to show that this will be equal to 1. Be the exponential form of L'Hopital's rule. The justification of this is that, well, as you go to infinity here, this is an indeterminate form. Specifically, it's going to infinity to the 0. It's a type of indeterminate form this is. Just like up here, this is negative infinity over infinity, this indeterminate form. So we deal with that by taking the natural log of both sides, which is valid as long as natural log is continuous, so as long as the arguments are all positive real numbers. So this will be the same thing as the limit as k goes to infinity of, or the natural log, I should say, the limit as k goes to infinity of the natural log of k to the power 1 over k, which is the same thing as the limit as k goes to infinity of the natural log of k over k, because the natural log to any exponent is the same thing as that exponent multiplied by the natural log of the base. And we just showed that this limit is equal to 0. So we have that what we're looking for, this limit right here, we have the equation the natural log of L is equal to 0, which means that L is equal to e to the 0, or 1. This is the reason why this limit is equal to 1. So you can use kind of similar methodology here to show a vast number of results, a couple of which are going to be very important to us in the future, such that the limit as k goes to infinity of any number x to the 1 over n, or 1 over k, is equal to 1. This holds for positive values x. The limit as k goes to infinity of x to the k will always be equal to 0 whenever the absolute value of x is less than 1. And probably one of the most important ones, the limit as k goes to infinity of 1 plus x over k to the k is equal to e to the x. This is another possible definition of this exponential function, e to the x. I'd like to go through and show this as well, because it depends directly on, right, it holds for any value of x, any real value of x. And the idea is that it's, again, relatively straightforward example of L'Hopital's rule. So as k goes to infinity for any value of x, this is going to be an indeterminate form of the form 1 to the infinity. So because of that, we're going to have to use some form of L'Hopital's rule. Specifically, if we take the natural log of both sides, the natural log of the left-hand side of this limit, and because the natural log is continuous for positive values of the natural log, and this value right here will be positive for us for larger values of k, as we kind of but this actually holds for any value of x. We can say that this is going to be the same thing as the limit as k goes to infinity of the natural log of 1 plus x over k to the power k, which will be equal to the limit as k goes to infinity of the natural log k times the natural log of the base, which is 1 plus x over k. And for any value of x, this is another indeterminate form. Specifically, k is going to infinity. 1 plus x over k as k goes to infinity is going to ln of 1 or 0. So this is an indeterminate form of the form infinity times 0. Or if we rewrite this a little bit, it's an indeterminate form of the form ln of 1 plus x over k over 1 over k, which is in fact equal to, from L'Hopital's rule, because this is now a 0 over 0 indeterminate form. This will be the limit as k goes to infinity of the derivative of this inner function with respect to k, which is 1 over 1 plus x over k times negative x over k squared divided by negative 1 over k squared. And so this limit, the negative 1 over k squared, cancel out, and the limit of this as k goes to infinity is just 1 over 1 plus 0. So this limit ends up being 1 over 1 plus 0 times x, or x, which means that the limit that we started the problem looking for is e to this value, or e to the x. And lastly, 6 will be very important to us when we get to Taylor series. The limit as k goes to infinity of x to the k over k factorial is equal to 0. So all of these limits can be proven directly, and they're very, very useful for computations. But we can talk about this. If you have any questions, let me know. That will conclude today's lecture. Thank you very much for listening, and I hope you learned something and had a great day.